Alright, in this video we will be talking about the concept of equilibrium. When dealing with equilibrium, we're looking at the fact that reactions can go both in the forward and backwards directions, and reactions will continue to look like they're progressing, and then it'll appear like they stop, but the reactions continue because things are not just going to stop colliding just because we call the reaction done. So what happens is whenever the forward reaction and the backward reaction are happening at the exact same rate, when we say that we have reached equilibrium. But it's a dynamic equilibrium in that the position of the equilibrium can change. Because if I change the pressure of the reaction, I might change the forward rate more than the backwards rate. Or if I change the temperature of one of the reactants for the forward reaction, then what's going to happen is the forward reaction will pick up in pace, but the backwards reaction won't, and so the reaction will continue forward again. If I change the temperature, it's going to change the rates of both reactions, but it will change the rate of one reaction more than the other, depending on if it's an endothermic or exothermic reaction. If it's an exothermic reaction, increasing the temperature causes the backwards rate to speed up more than the forward, and so on. Okay, so these effects of how we can change the position of equilibrium is known as LeChatlier's principle. Okay, and LeChatlier's principle basically says, and then this is just more on like things to consider for equilibrium. Sorry, but LeChatlier's principle basically says whatever you do to a system that's at equilibrium, the way that the rates of the reactions will respond to that will cause the reaction to counter what you just did. And it's not that the reaction is trying to be recalcitrant and say, well then, you added more hydrochloric acid, so I'm just going to take it away. It's just that the reaction is, if you add more hydrochloric acid, the reaction that takes it away is going faster now than the reaction that replaces it. And so it will reach a new equilibrium that partially undoes the change that you made, or at least attempts to. Okay? And so here's like an example that we can look at. If I have this reaction of nitrogen reacting with hydrogen gas to make ammonia gas, if I look at some different things, so like if I increase the pressure of the container once it's reached equilibrium, what that will do is, if I increase the pressure, it brings everything closer together, and so they collide more, and so it makes both reactions faster. But since the left side has the left side has a total of 4 gas molecules, and the right side has a total of only 2 gas molecules. Increasing the pressure will speed up the forward reaction away from those 4 gas molecules a lot more than it will speed up the reaction of just the 2 gas molecules coming together to go the other way. Okay? If I increase how much nitrogen's there, what's going to happen then is, if I have more nitrogen around, the nitrogen is going to collide with the hydrogen more often, and that's going to speed up my forward direction. So, in effect, when the forward direction speeds up, it's going to then decrease nitrogen. Okay? So, increasing, I don't know why that goes away. So if I increase pressure, that's going to make it go forwards more. If I decrease the pressure, that's going to make it go backwards. Okay, if I increase how much nitrogen present, again, that's going to make it go forwards. If I increase the hydrogen, for the same reason, it's going to do the same thing. If I decrease the amount of ammonia, then it's going to make it go forwards also. Okay, it's going to make it go forwards because now it's going to want to replace. Because if I decrease the amount of ammonia, it's going to slow down this backwards reaction, but the forwards reaction hasn't slowed down, so it'll continue on. All right? And so there's some more examples here that I probably don't have time to go through all these in class, or sorry, in the video. We can certainly go through them in class of what might happen when you do some different things to these different reactions. Okay? Equilibrium, not just in reactions, can also occur between different phases of matter. So if you look at, for example, like salt that's solid, so when you have a crystal of salt then you also have salt in solution. There's a certain rate that the salt is dissolving at, and that the ions are coming together to make a salt. So equilibrium can exist in that way. It can exist between like liquids and gases, and if you look at evaporation, because there's always whenever you have like a pool of water, it's not just evaporating, it's also recondensing. So the question is it evaporating faster or is it recondensing faster? And that's going to control whether or not that pool of water disappears or stays there or gets bigger. Okay? So in terms of quantitatively dealing with equilibrium, we found you can show that when the forward rate and the backwards rate are equal to each other, then the way the concentrations are related to the concentrations of your products and your reactants are related to each other is by a somewhat simple expression. And if this is my generic reaction, A's plus B's, so these are like my coefficients, and this A is my, like what substance I'm talking about. If this is my reaction, then the equilibrium constant for this, the way that the A's and the B's and everything will be related to each other at equilibrium will be given then by this equation. And we'll see how to use this with a real reaction, because I think for now it's like, oh, what's up with all these A's and B's and things. Okay, so we're going to look at how this applies. Okay, and again, just before we go to apply, the reason why this happens is because at equilibrium, the forward rate of reaction equals the backwards rate of reaction. And so the forward rate of reaction is given by this rate law, and the backwards reaction is given by that rate law. And so when those two rates are equal to each other, you can rearrange that and find that the way the concentrations of everything are related is equal to the ratio of forward rate constant to backwards rate constant. So now let's look at like an actual reaction and see how this applies. So I've got a reaction of 2 nitrogen dioxides goes to dinitrogen tetroxide. Okay, and if I was to write the K for this, I would write that K equals, and again it's going to be a ratio, and the ratio is always going to be products. I don't know why I didn't write this on an earlier slide, over reactants. Okay, and so my product, we always just, even again, we're talking about reactions going both ways, but still convention is to call what's on the right side the product. So products, I'm going to look at the concentration of N2O4, and that's to the first power, because there's only one N2O4 in my reaction, over the reactants, NO2, and that's going to be squared because there's 2 NO2s participating in the reaction. This is going to always equal a constant number. So if I want to know what that K is, I do my reactions and I put in some different amounts of NO2 and I put in no N2O4 and I let it react, and then I find once it reaches equilibrium and it appears to not be reacting anymore, I have these new equilibrium concentrations. If I take and stick those equilibrium concentrations into the formula I found here, I find that K should equal 0.00140 over 0.0172 squared. Now I do another reaction, and this time I start with 0.03 instead of 0.02, and it comes to equilibrium, and I have 2 new equilibrium concentrations. If I put those into K, I'll get that it equals 0.00280 over 0.0243 squared. Now, put those numbers into a calculator. Find what it comes to. You should find that the K in both these cases are equal. Even if I start everything over as N2O4, comes to equilibrium. When I put them into the expression, you should find that it equals a number. I think you should find K equals, if I remember, like 4.7 something. Okay? Now, sometimes we want to know if I put 2 things together, are they at equilibrium or not? Okay? And so for that I use what's called the reaction quotient. Okay? And the reaction quotient is the exact same thing as K in the way we write the formula. The only difference is if I was writing K, then these would be equilibrium concentrations. When it's equal to Q, then these are not equilibrium concentrations. They're just arbitrary concentrations. When I do this, if I find that Q is less than the equilibrium constant, what that means is that I have way too much reactants, okay, and not enough products. And so the reaction has to go forward to reach equilibrium. If I find that or that Q is greater than K, it means that I have way too much on the product side, and it needs to go backwards to reach equilibrium. And if Q equals K, that means I have just the right amount of stuff, and so then it will, it's at equilibrium. It won't do anything. I mean, it's still doing something, but you can't see that it's doing anything. So here's an example where we know that for this reaction, K equals 50.5, and we want to know what direction we'll go if we have these conditions. So I set up Q. Q equals HI squared, because of the 2 here, over H2 times I2. So I'm going to put in all these numbers here. Okay? And what I want to see is, once I put in all those numbers, do I get a number that's greater than 50.5 or less than 50.5? Okay? So again, I want you to do that on your own and see, do you get a number bigger or smaller than 50.5? Okay? Now, what we just did only tells us if the reaction is going to be going forward, not how much will it go forward, or if it's going to go backwards, not how much. In chemistry, oftentimes, it's not just good enough to know, will it go forwards or backwards? We need to know how much. Where will it actually end up? And to do that, we use what's called an ICE table. We look at how much stuff do we have initially, how much do we have, how much is it going to change by, and how much is at equilibrium. So in this problem, I'm starting off with 2.00 molar SO2. I'm reacting with 1.50 molar of O2 and 3.00 molar of SO3. And if the K is 4.32, I want to know, how will this get to equilibrium? Where will it end up going? So I know the initial conditions. I don't know how much it's going to change by. But I know that, let's say, if oxygen is going to go down by some X amount, then SO2 has to go down by some 2X amount, because of the ratios are 2 to 1. Okay? And whatever amounts these, if O2 goes down by some X amount, then SO3 has to go up by 2X. Okay? So, and again, by stoichiometry, whatever this one goes down by, this one goes up by. And the reason why the opposite signs, if these are my reactants, as the left side's being used up, the right side's being created. So at equilibrium, I don't know what X is, but I know it'll be 2 minus 2X. I don't know what X is, but I know this one will be 1.5 minus X. And I know this one will be 3 plus 2X. So now, if I look at my equilibrium constant, what does it equal? It equals SO3's concentration squared over SO2 squared times oxygen to the first power. Now I plug in what I do know. I know K is 4.32. Okay? I know SO3, I actually don't know what it is, but I know it'll be 3 plus 2X squared. For SO2, okay, I know it's 2 minus 2X squared, and for O2, it's 1.5 minus X. Now, if I can solve for X, I can plug X back in and figure out, hey, what are the concentrations at equilibrium? Now, here's the deal. That is hard to solve algebraically. Not saying it can't be done, not saying you never would have to do that in an algebra class. But here in science class, we're like, we know algebra exists, but guess what? You can plug this expression, as long as you do it carefully, into wolframalpha.com, or if you have a nice graphing calculator, you can put it in your graphing calculator, and it will solve it for you, and you'll find what X is. And when you're trying to figure stuff out as a chemist, that's what you do. You don't sit down and spend a half an hour on the algebra. You just know you have tools available to you, and you take care of it. And that's what you'll do for this class too. And in fact, all I care about, can you set this up? Okay, we'll talk about in class, I'm running out of time here, but we'll talk about in class, sometimes you can make approximations. And we'll talk about those approximations in class and what that allows you to do. Okay, so for now, we just have to know how to set up, and we'll talk more about this tomorrow in class.